Okay. Hi, guys. So welcome to Introduction to R, Python, and Flow. So this will be sort of the first simple hands-on that you guys will have today. And I'm going to try to go over not even the full data science workflow, but just to get you started running either in R, Python, and Flow. Like Vinod mentioned, I'm sort of a sales engineer at H2O, and I will be in the audience later if you need help to install and run some of the demos I just shown. So feel free to catch me later. So today we're going to get started on learning how to use H2O from different clients, R, Python, Flow, which is our web-based UI. And we'll go over some directly how commands are sent from all these clients into H2O to execute in a distributed and parallelized fashion. And then we'll go over some quick Q&A or frequently asked questions about the R package and the H2O Python module. And then jump into the hands-on demonstration of how you would run a model build on a data set and review the model outputs and talk about how you can improve upon the very simple workflow that you currently have in all your laptops. So again, for this tutorial, you're going to have to either have H2O installed, R installed, or Python installed. I am going to go through the same workflow on 3 different platforms at the same time. So you just have to have one or the other installed and pick and choose your poison, essentially. So if you're comfortable in R, run the R script. If you're comfortable in Python, run the Python script. So quickly, as an example of how something like data is read into H2O from R, the R user will essentially execute a R function call, and the function call will tell H2O to import the file and give it the path of where the data set is sitting. So the function call, R function call, is then sent over through the H2O REST API, which is uniform across all the different platforms. So even though I'm talking about R, it goes the same for Python and Flow and any REST API that client that talks through the REST API. The argument gets carried over to the H2O cluster, which subsequently requests the data from this and this locally to the cluster, not to the R client. So in our instance, we'll be running locally on your desktop, so that this is local to your desktop. But if you're on launching an H2O cluster on Hadoop, for instance, you'll be reading in data from, say, HDFS. Then data subsequently is read into H2O in a parallel read into memory. And then the distributed data frame is actually summarized, and all the summary statistics is then passed back into R as a JSON response, which we parse in R. So we'll parse all the information and then turn it essentially into S4 into an R object, which we call H2O frame. It looks and feels like a data frame, with the exception that it's only a pointer to the actual frame sitting distributed on the H2O cluster. And here's another example of how R calls H2O to build a GLM model, for example. So this is in more detail the communication layer between R and H2O. So essentially, you will have you're going to start up your standard R process, which we'll call the H2O.glm function, which gets translated to a REST call to start a GLM model build, which carries through a TCP layer into H2O to start up the H2O MapReduce task or H2O magic to run really quickly in H2O and then return back into R to process. And so one of the common questions that I get asked about R is, does H2O support all of R's many packages and functionalities? And the quick answer is no, we don't. There are a lot of great things we built into our robust R package, but there are also limitations as well. So we have here a very quick sort of summary of R and as well as Python parity to whatever you might currently have in R or scikit-learn, which is essentially you will replace functions like read.csv to H2O.import file. Summary will work the same. You can bind columns and splice them. There are unary and binary options are also supported. but we do not support all available packages out there. So something, for example, like Smooth, we do not have the analogous version of that in H2O R. And so subsequently, things like the Caret package, you can't just load up Caret and try to execute it on an H2O frame. But if there are anything that are high requests, H2O is really great about adding functionalities. All these functionalities you see on the R on H2O side has actually been added in as people request them as necessary parts of their workflow. So please, communicate to us if there's anything that you think is missing from our package. So really quickly, going into the airlines demonstration, everyone uses airlines, but it's a good starting point, and we've used it since 3 years ago, so we'll start with that. So with the tutorial, we're going to simply import and parse a small 44,000 row airlines data set. We'll build a simple logistic regression and a deep learning model to predict departure delays based on the historical data, review the output of the models, explain why we have such good results or bad results, and then you can tweak it going forward. So there's 3 ways to start this. First, for flow users, you would essentially need to start up the H2O jar file. So on your terminal, once you have the H2O jar file, just execute java-jar h2o.jar, and then access flow at localhost 54321. In R, if you have the script open already, it should just be library h2o, h2o.init, and set end threads equals to -1. So one quick note for our users is when you initialize a connection in R, by default, we will take 2 cores of your machine. So when you set end threads equals to -1, it will utilize all the cores of your machine. So it's a small point, but an important point to drive home. And in Python, import H2O, and then again, an h2o.init function. So I'm going to show really quickly what the Python Jupyter notebooks looks like for this tutorial. So it'll start up with predicting airlines delays in Python. It'll have links to the small data set that we have, as well as larger scaled up versions of itself. So you can go home and actually run this on larger data or big data. And then going down, you have cells that I'm going to ask you to control enter and execute as we go along. Same thing with R. You'll have a intro to R md.r file that you have on your disk, and essentially you would just load it up, and to execute, instead of cells, you're going to have lines of code, so you can highlight these lines of code and just control enter, and you'll see I'm already starting up H2O, and in my instance, the time it takes to build models and read in data might be slightly different because I have an 8-core machine, just to keep in mind. And subsequently, for Flow users, we already have a pre-installed pack in Flow. It's on the right-hand corner of at localhost 54321. You can view example flows. And we have here already available a list of demonstrations that we've already built into H2O by default. So once you go home or later on, you can run any of these tutorials, run a deep learning model predicting digits for amnest, or run a GBM model predicting arrhythmia. So all of that's already available in Flow. But in our particular case, I would like you to choose airlines_delay. And Flow will ask you whether or not you want to load the notebook. Please say yes. And we'll have something to get started with. So first, we're going to import the airlines data into H2O. The Flow and R and Python commands are syntactically different, but essentially it's just a function call with the argument in it that tells H2O to execute in a parallel and distributed fashion. So our users, one quick note is the data set path is relative to where you have your R notebook open. So here I've normalized the path so you get the absolute path, but make sure your working directory is set to whatever working directory the script is sitting in. So it should be intro to R, Python, and Flow that directories, and then it'll automatically read in the data. So I'm going to show you really quickly what that looks like from Flow, and people please point and click along in here, view Flow, Airlines Delay, load notebook. Yes? Oh, sorry. So we're just going to import the file, set up the parse for it. So in Flow, the notebook will automatically download the data from Amazon. It's a small file, so it shouldn't take very long at all. It'll take about 6 seconds. It'll parse the file, and let's see. Okay, there you are. So it'll give you a summary of what the data looks like before you actually hit parse. You can either hit parse or just go to the next line and Control Enter, and it will start parsing the data into H2O. So this in R and Python is essentially 2 cells or 2 lines of code, and the MD file should make it obvious which lines of code that is. You can do a simple get summary, frame summary, and so it'll give you everything from all the columns to the type the columns are imported as, min, max, mean, and for categorical columns, you can actually look at the frequency of each of the levels in the column. So something like, let's say, destination, you can see really quickly the first one to come up is Phoenix for some reason in this data set. It's the first, the most frequent category in this column. So once you have the data imported in H2O, the next step is to basically build a model predicting departure delays using the historical airlines data set. So the enumerated columns that are of importance is the destination, the origin, and the unique carrier the flight is using. And they each have, in this particular data set, a cardinality of 134, 132, and 10, respectively. And what H2O does is we automatically do the categorical expansions into its dummy variables in the backend for you, so you don't have to do one-hot encoding or expand it out to a model matrix yourself. So all of that's done automatically for you. We're also going to use the day of the week, day of the month, year, the month, and the distance of the flight. These are numeric columns in our data set. And we're going to predict for the binary response column, is depth delayed? Here we go. So again, Flow, R, and Python users find the code that is necessary to run the GLM model. In Flow, it'll just be a cell build model GLM. In R, you define the y and x variables and all the different parameters as arguments in the H2O.glm function, and then just execute that, Control Enter. Python execute the cell that has the y and x variable defined, and is using the H2O generalized linear estimator class. And then subsequently to train it, just do GLM model train. So all of that's already available in the notebook, so that shouldn't be a problem. So let's run it through Flow really quickly. And this will take about 4 seconds on my laptop, about 6 iterations. Here we go. And we're going to get the model real quick. This is on my slide as well, but on this particular data set, in about 4 seconds, we have an AUC value from a logistic regression model of around 0.8. In particular, in R and Python, you can graphically pull all of this into R and Python and plot it. But in Flow, you can always get a really quick view. And for each of the threshold on the ROC curve, actually, we have a dynamic printing of all the confusion matrices for all the different thresholds. So you can choose, let's say, the F1, max F1 threshold, and it'll have a new confusion matrix printed out for you. So all of that is available through Flow. Going down, we have the standardized coefficient magnitudes, the scoring history, so the objective value over the number of iterations that you ran. And let's see here. What's actually important is the metric itself, so everything from the mean square error to the AUC value and this residual deviance. I think all of that is shown actually here. So you have everything from the residual deviance, which is probably what you would use to compare GLM models from some H2O to, let's say, GLMNet in R. And you can compare the residual deviances and see which model actually does better, or at least they're comparable. So I've inputted a lot of parameters. I ran it with standardization by default, and by default we run it with some regularization. And so a lot of those parameter tunings, if you're interested in learning more about how to tune GLM, Tomas Nicodem is having a talk at 10:45 at the other stage, and 2:15 at this stage if you're interested. Then subsequently, we're going to build a deep learning model. And this one, we should really start basically ASAP, because it will take, I've set it up so that it runs for 100 epochs. It will take about 2 minutes on my laptop. And so just talking through it really quickly, I'll show you the results before the model actually finished running. So you'll see here that it'll take significantly longer to build the deep learning model. I've set it so that it'll run for 100 epochs. It means 100 passes over the data, which is relatively small. And you'll see that we have an AUC value of around 0.95, or actually 0.96 almost. So this looks great, but it falls into one of the trappings that Aaron mentioned earlier, which is overfitting a model. So here we didn't do a test train split for something like deep learning, which very easily overfits. So in the future cases, I would recommend in your workbook to do a test train split, so you actually, the AUC value is not so artificially good. And so it's still running. But the interesting thing is, as it's running for deep learning, you can actually get the model already. So see, right here we have 0.91. So as the model is building itself, you can actually refresh it, and it'll give you an updated view. So the AUC continues to improve. And down here, you have the scoring history of the mean square error over the number of epochs. And we're still on 60, but the model has basically almost pretty much come to the maximum AUC it can come to. So there's that. In R and in Python, let's see. To execute the GLM and GBM model build, I would just want to show you really quickly. It's, again, like 5 lines of code. So you just Control-Enter, and it will build the model. And you can compare the model built from R and Python versus the one that we built from Flow. And the default parameters should be the same, so the models itself should be the same. But as you execute commands in R and in Python, because everything's pointing to the same H2O cluster through the same REST API, you can actually look and review the models and frames that you're creating in R and Python in Flow itself. So you have all the programmatic functionalities of R and Python, but in addition to that, you have a graphical interface like Flow to occasionally sort of gleam at really quickly. So let's see if we finish building the model. Yeah, took about 2 minutes and 7 seconds. And we'll just refresh this really quickly. Voila, 0.95. Yeah. And I haven't set it here to actually show the variable importance, but for GBM in particular, it might be interesting to run that with variable importance turned on. So you can see which one, you can do variable selection that way, or and again, if you're interested in learning more about deep learning, Arno, who was on stage earlier, will talk about his deep learning function and algorithm here at 1:30 and at the larger stage at 5:45. So overview, to write R and Python expressions, usually people write R and Python expressions to clean and munge the data, to do simple group bys, splice the data, subset it, and subsequently basically clean the data ready for model build. But then you can write R, Python, or Flow code to automate the model build process. And because all the frames and models, like I said, are generated in H2O, is all accessible from the Flow UI. And from the Flow UI, one thing I haven't showed you yet is that the user can easily access the plain old Java object that is the model output that you will put into production, which let's see if I can show you here. So something as complicated as deep learning, you can preview the POJO, and you'll see all the activation weights, everything is hard-coded into the model output. And this is essentially what you would take and build applications around. And we have many talks today, including one by Tom Kraljevich, one by Mikhail Malaholova, in building web applications and sparkling water applications around this POJO. And so it's essentially our nano fast scoring engine, and that can be compiled completely outside of H2O. I think that is it for me. Let's see. Here we go. So if there's any other, that's the sort of introduction into H2O, R, Python, and Flow. If there's any questions or yes. Hi. Do I do any cleanups? Yeah. So there's actually a talk later about munging the data set and creating a pipeline in Python to do all that munging work, or in Spark in particular. In this particular case, I didn't really munge the data. The airlines data comes pretty clean. But we have scripts online available to do to show you how we munge the data to do what we want. Anything else? Yes. 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 Oh, yeah. Oh, actually, yeah, I should mention, sorry. Thank you. That's a really good point. So this is why, actually, it should be is what the operative word was. But if I execute this model right here, and it won't overwrite the one I built before because I called it something else, GLM model from R. Let's see. Oh, yeah. Okay. So the question was, when you're running the GLM model from Flow, someone was getting a different AUC value in the GLM model that's produced in Flow versus the one in H2O. And so I'm just going to get frame. X. There we go. Summary. And we'll build this model real quick. It'll take about 4 seconds. Yeah, there you are. And AUC value, here we go. Yeah, I'm getting 0.74 in this particular case. So I think there is one tuning parameter that is not exposed to the front end in R that the default is set differently because it has changed recently. So good catch, and we will fix that. Let's see if I can pull up host. Get frames, get models. So you can look at the GLM model from Flow and then the GLM model from R. You see that the AUC value is indeed different. But then you can look at the model parameters, show all parameters. I think it was in particular, I think it was the gradient epsilon that was different from the one in R model. Gradient epsilon. Yeah, so for one, it was actually 10 times lower than the other. And then again, if you want to know what any of these parameters mean, go to Thomas' GLM talk in a little bit. But yeah, there was some changes in default parameters. So make sure to notice these things when you're playing between R, Python, and Flow.
If you have any questions, raise your hand. I'll come around the mic.
Yeah, I'm good. I'm done. Perfect. I finished on time.
All right. Thank you, Amy.
Thank you. Let's see. Oh.